Good morning. In this lecture video, I'm going to explain Zener Diode as a voltage regulator. So, these are the components of power supply, typical power supply. So, we discussed the filter, okay, in the previous video, and this is the output of filter, and that is applied as an input to the regulator, and the regulator output is steady state, DC output, constant output. So here there is a small change, variation. It's called triple voltage, and that becomes converted into a constant output. So how do we convert? Using a regulator. Okay. So this is unregulated output. We get regulated output. To get this regulated output, we use Zener diode. So first we'll see what is Zener diode. It is a symbol of Zener diode. Again, it is a PN junction, a special type of PN junction diode. This is anode and cathode. It is a special kind of diode which permits current to flow in the forward direction as a normal, as well as also permits current flow in the reverse direction when the voltage is above the certain value. That value is called as breakdown voltage, also known as a Zener voltage. Okay, so when the voltage is above the Zener voltage, it also permits the current to flow in the reverse direction. And Zener diodes are highly doped PN junction. As I said, it is a PN junction diode. These are special characteristics. They are highly doped PN junction diodes. So the diode, which can be operated continuously in a breakdown region without any damage being caused to it, and operates in the reverse bias condition, is called as a Zener diode. So Zener diode is the diode which operates in the breakdown region without damaging the devices and operates in reverse bias condition, is called as Zener diode. And this is a practical available in the symbol. Okay, so this block is there, that is a negative, another one is a positive, so anode and cathode, and this is the symbol. Now we'll see how we can use this as a voltage regulator. Remember, voltage regulator means it has to give constant regulated DC output. So it can be used as a regulator since it maintains a constant output voltage even though current through the Zener changes. So this is, let's see the circuit diagram. This is the input voltage or supply voltage, variable voltage, and this is Zener diode. One resistor, that is called current limiting resistor, so RS, and here current through this is I, and current through the Zener diode, let it be IZ, and we connect one load resistor RL. Current through this is IL, and we consider output across the RL. This is the circuit, Zener voltage regulator. Okay. So that means circuit consists of unregulated voltage source, that is VA. It is not constant, unregulated, and current limiting resistor RS. The third one, Zener diode, is in parallel with the load resistor RL. This Zener diode is parallel with the load resistor RL. Okay. So Zener should be selected such a way that the required regulated output voltage should be greater than or equal to Zener breakdown voltage. That means, suppose if you want constant output voltage of 6 volt, okay, so we should select a Zener of breakdown voltage 6, and for the condition first must be followed. First condition, Zener diode must be reverse biased. So see, so the circuit diagram, it is reverse biased since cathode is connected to positive supply and anode is connected to negative supply. And second condition, input voltage must be greater than the Zener breakdown voltage. That means this one, input voltage, it should be greater than. Suppose it is a this diode is a of breakdown voltage 6 volt, it should be greater than 6 volt or it should equal to 6 volt. Then third condition, load current, that means current through the IL should be less than the maximum current through the IZ. So here this is the current I, that current split. Okay, here some current will flows to IZ and some other current flows to IL. Okay, so this IL should be less than the IZ maximum current. And generally, most of electronic applications requires very low Zener current output. So circuit has implied voltage reference source that supplies only very low current. So resistor is used to limit the Zener diode current to the desired value. So now let's see without no load. I mean we are not considered a load. Okay. So this is the circuit without a load. Without a load. So in this circuit, current through the resistor is also same IZ and the same current is passed through diode, Zener diode. And this is the current flow. Now we'll apply current KVL, Kirchhoff voltage law, to the loop. That means KVL is states that in any closed loop, algebraic sum of voltages is equal to 0. So in such case, the equation VI minus uh, IZ into RS, so that is voltage across the RS, and voltage across the Zener diode is VZ is equal to 0. So from this equation we can derive the expression for IZ. So IZRS is equal to VI minus VZ. So IZ is equal to VI minus VZ divided by RS. And minimum current is obtained when the VA is minimum. So IZ minimum is equal to VA minimum minus VZ divided by RS. We will maximum current when VA is maximum. That means VA maximum minus VZ divided by RS. So now we'll see a regulator with load. With load, this is the circuit with load. We consider voltage across the Zener diode is VZ. Again, this is the closed loop. Now current through the limit current through the limiting resistors, that is RS, is sum of current through the IZ, Zener diode, and current through the RL, that is IL. Okay, but here we must take care to ensure that IZ minimum is greater to keep the Zener diode under breakdown voltage. So total current should not exceed the maximum current to the Zener. So let's consider this is the node. This is the node. Okay. So to this node we apply KCL. KCL is the node A. You know KCL is states that algebraic sum of all currents entering and exiting a node is must be equal to 0. Otherwise, current entering into the node is equal to current exiting from the nodes. That means I is equal to IZ plus IL. I is entering current, IZ and IL are exiting current. Okay, so again applying KVL to the closed loop. So as we observe, VI minus current to the current limiting resistor I into RS minus VZ. So from this again I, the expression for I, that is IRS is equal to VI minus VZ. So I is equal to VI minus VZ divided by RS, and I is equal to IZ plus IL is equal to VI minus VZ divided by RS. This is the total current. Now, as you know, regulator performance, okay, it is defined or expressed in terms of source and load effect and line and load regulations. So source effect means what is the effect of source? When the source is changes, what will be the effect? Consider this is the circuit, regulator circuit with no load, and this is the corresponding AC equivalent circuit. That means here diode is replaced with the dynamic resistance. That means ZZ. So consider AC equivalent circuit with no load drawn by replacing diode with its dynamic input impedance. It's input impedance, that is inverse of resistance ZZ. The circuit seems to be a simple voltage divider. Okay. So the applied voltage is divided into voltage across the RS and voltage across the ZZ. So when the input voltage changes, I mean small changes in input voltage represented by delta S, there will be small changes in output voltage, that is across the uh, impedance ZZ, that will be delta V naught. Okay. Then output changes is expressed as change in input voltage, that is delta Vs, into the voltage, the impedance ZZ divided by total impedance, that is Rs plus Z. Z. This is change in output voltage. So we are changing uh, source, source voltage, and what will be the corresponding change in output voltage? That is expressed as change in delta Vs, that is change in input voltage into ZZ divided by total resistance Rs plus ZZ. So when there is a load appears in parallel with ZZ, that means you. Okay. With this is the circuit with the load. Again, the equation for output changes is delta Vs into ZZ parallel with RL. So these two are RL divided by total resistance Rs plus ZZ in parallel with the RL. So source regulator source effect can be determined either from this equation or from the previous equation. This is the source effect. Okay. So line regulation means, let's consider the regulator with a load. That means here load is constant. The series resistance and load resistance are kept constant. This is series resistance and load resistance are kept constant. Variation in the voltage is due to fluctuation in the input supply. That means we are changing the input voltage. So the regulated output voltage is achieved for the input voltage above a certain level. That level is called as a Zener voltage. So the percentage of regulation is given by change in output voltage divided by change in input voltage into 100% in terms of percentage. So V naught is the output voltage, V in is the input voltage, and delta V naught is the change in output voltage, and delta V in is the change in input voltage. Okay. Now we'll see load effect. Load effect. So again we consider this is the circuit without a load. Okay. So it is a equivalent Thevenin equivalent circuit of this circuit. Again, to determine the load effect, circuit output resistance to be calculated. So this is the Thevenin equivalent circuit, assuming a zero source resistance. Circuit output resistance is R naught, effective resistance of output. R naught is equal to Rs parallel with ZZ. Okay. So when the load current changes by delta L, this one, okay, changes by delta L, output voltage changes is equal to V is equal to IR. So output voltage delta V naught is equal to delta IL into the total resistance, that is ZZ parallel with the RS. And load regulation, in this case voltage is fixed. Voltage is fixed while load resistance is varied. If we change the load resistance, what will be the changes in output voltage? So constant output voltage is obtained as long as load resistance is maintained and above minimum value. So percentage of regulation is given by V no load VNL minus VFL divided by VNL into 100%. Here VNL means voltage across the Zener diode when no load is applied, and VFL means voltage across the Zener diode when full load is applied. So this is about the performance of regulator. So we'll continue the next video. Thank you.